Hello, my name is Andrea Correia. I will be presenting OrcGC Automatic Lock-Free Memory Reclamation, a work done by myself, Pedro Ramalhete and Pascal Felber. I will start by introducing some definitions. After, I will present our new manual reclamation Pass the Pointer. I will also present our new automatic reclamation OrcGC. And finally, I will present the performance of our two memory reclamations against existing memory reclamation schemes. I will start by introducing some definitions. A global reference is a reference stored in a variable that is always accessible by all threads in the system. A local reference is a reference only accessible by a single thread. An hard link is a reference to a shared object that is stored in another shared object. An unreachable object is an object that cannot be accessed through a global nor local reference. Here is the code for Michael and Scott lock-free queue, where we can see the global references, the hard link, and the local references. An example where we have multiple nodes inserted in the queue. We can see that C, D, and E are reachable nodes, but A and B can be later deleted. Here are some lock-free memory reclamation schemes. A scheme can be manual or automatic. The main difference between a manual and an automatic scheme is that when using a manual scheme, the user must identify in the code the point from which an object has no hard links to it. For some algorithms, it may not be possible. An automatic scheme, on the other hand, will detect when an object can be deleted automatically. Before OrcGC, the only available automatic scheme was free access. Another difference between memory reclamation schemes is the allocator it uses. For example, free access uses a custom allocator. This allocator pre-allocates a large chunk of memory and where the lock-free algorithm runs. This is necessary because free access allows threads to read memory locations that were previously deallocated. If it was to use an allocator that manages a memory as a whole, where it could share chunks of memory between processes, this could lead to a segmentation fault. I will start by presenting the memory reclamation scheme Pass the Pointer. Like other lock-free schemes, Pass the Pointer implements two methods. The method getProtect, that must be used by a thread to protect an object before dereferencing it, and the method retired, called when an object has no hard links that refer to it. After retired, the object is deleted when it becomes unreachable. The getProtected method is implemented in the same way as in hazard pointers scheme. The difference is in the retired method. PTP uses an array of hazardous pointers where each entry is assigned to a thread and an array of handovers shared by all threads. For each hazardous pointer entry, there is an associated handovers entry. On the hazardous pointers array, it is stored the address of an object that was previously protected. The handovers array is where a retired object is placed if there is an hazardous pointer to it. Now I will show an example where thread T0 will retire A. The thread will start by searching for A in the hazardous pointer. It has located A on thread 1 and replaces on the handovers array what was previously there with A. Because it is null, it stops the execution of the retired method. When an object is retired, the retire method must validate if the address of that object is published in the hazardous pointers array. If an hazardous pointer is found, the object is placed in the associated handovers entry with an exchange instruction. If the previous value is null, the retired method ends. Otherwise, it will continue with the new method with the new value from this point on, searching for on the hazardous pointers array. It will only delete the object if no hazardous pointers are found. On the example, we can see that thread T3 is trying to retire B. It searches on the hazardous pointers array if B is published and finds it published by thread T1. Then it will exchange B with A on the associated handovers entry. Now it has A, the address of A, and object A might not be published on the hazardous pointers array, and maybe it can be deleted. So it will continue searching now for A, if A is published in the hazardous pointer from this point. So it doesn't need to restart from the beginning of the hazardous pointer. Only from this point on, it must continue the search, because it is guaranteed that thread T0 cannot publish the address of A successfully. Now it continues and it found again A published by its own thread. So it exchanges, and when it is null, so the retired method ends. This slide is to show the difference on the implementations of HP versus PTP. The get protected is implemented in the same way, where the address is read, is written to the hazardous pointer, and then revalidated if it has not changed. The main difference is on the retired method, where on HP there is a retired list dedicated to each thread, where the object is placed, the objects that are to be retired. On the other hand, for PTP, it's the handovers that where the objects are placed and are shared between all threads. PTP implementation allows it to have linear bound on the number of unreclaimed objects, because each thread can only have one outstanding object to be deleted. This is not the case of HP, where each thread can have max thread objects waiting to be deleted, which gives them a quadratic bound. PTP has also lock-free progress. The retired method has no infinite loop, and the get protected will only fail to publish if another method changes the address it is trying to publish. Now I will give an overview of OrcGC, our automatic memory reclamation. To reclaim memory, OrcGC must detect when an object becomes unreachable. For that, it combines per object reference counting with a pointer-based reclamation scheme. The reference counting is used to count the number of hard links to the object, and the pointer-based reclamation scheme tracks the local reference to the object. OrcGC integrates PTP as its pointer-based reclamation scheme. It provides linear bound on unreachable objects for algorithms that do not form chains of unreachable objects. In case there are cycles of unreachable objects, that memory will be leaked. OrcGC has lock-free progress. In order to track the number of hard links to a shared object, every shared object must extend OrcBase. OrcBase has a member _orc, and that's the variable that keeps the counter. _orc is composed of the first 22 bits, where the counter is kept, after the 1 bit that indicates if the object is marked to be deleted, so if the object is retired,
named be retired, and the remaining bits is where the sequence is stored, and the sequence changes every time the counter, the first 22 bits, change. If the counter, the first 22 bits is OrcGC, it indicates there's no hard links to the object. All shared variables must be declared OrcAtomic instead of stdatomic to allow the Orc variable to be updated every time an hard link changes. We can see an example, for example, of the compare and swap operation, that it is first the root pointer is pointing to object A and will change to refer to object B. This means one less hard link to object A and an extra hard link to object B. Also, every time a shared object is created, it must be by calling make arc. Every time an atomic load or make arc is called, the local reference it returns is automatically protected by an hazardous point. These operations will return an OrcPTR object that will include the local reference and the index where the hazardous pointers of this reference is kept. This is an example on how to annotate Michael and Scott Q with OrcGC. So the node must extend OrcBase. Every time a new node is created, instead it must call make arc. The next and add and tail that are hard links must be changed from stdatomic to OrcAtomic. And every time a load is called, it is stored in an OrcPTR object. As soon as an object has no hard links to it, it must be retired. Or in other words, if its Orc value reaches OrcGC. The thread that has changed the Orc value to OrcGC is the one responsible to retire the object. For that, it must change the be retired bit to 1 with a compare and swap, and if successful, call the retire method. It's interesting to notice that the underscore arc variable may transition from OrcGC to a positive or negative value. This happens because of our implementation on the compare and swap, where we first execute the compare and swap that was requested, and only after, if it's successful, we change the arc on the new value and old value, incrementing the arc on the new value and decrementing on the old value. Because the hard link is made accessible before the arc on the new value is incremented, this allows for other threads to possibly remove the hard link again and decrement the counter before the increment is executed. An object can be incorrectly retired. Its arc value can reach OrcGC temporarily. There are two scenarios where this can happen. A thread holding a local reference to the object later creates an hard link to it, making the object accessible from the global references, and the arc count update is delayed relative to the hard link change because of our implementation on the compare and swap, where the hard link is made available before the arc is incremented. As soon as the thread responsible to delete the object detects the object was incorrectly deleted, so its arc is no longer OrcGC, it must atomically reset the be retired to 0. This will make the object no longer a retired object. An object can be incorrectly retired, but never incorrectly deleted. For an object to be deleted, it must have, at a point in time, no published hazardous pointers to the object and no hard links can refer to the object. In other words, the object must be unreachable. In the example below, we can see that thread 2 has an hazardous pointers published for node A, and head is referring to node A, so A has an hard link to it. Also, node B has two hard links, next and tail, so arc is set to 2. Both head and tail are global references. Now T1 is inserting node C, node D, and node E. Now T3 will start by dequeuing node A, B, and C. At this point, the global references head and tail no longer can reach A, B, and C, but these nodes are still reachable through T2 that has a local reference to it, to node A. The only node that can be retired at this point is node A that has arc at 0, but cannot be deleted. There is still another pointer published in for node A at T2. Once this local reference disappears, then node A can be deleted. And to validate this, the arc must be at 0 at the start of the traversal of the hazardous point and at the end, and the sequence associated with the arc cannot change. Once this is validated, then node A can be deleted, and when the deletion is called, it will call the destructor of A, that in turn will remove the hard link to B, that will cause the arc of B to reach 0, that then will be retired, and so on. This could cause a stack overflow. To avoid this, our implementation, instead of calling recursively the retire, will put the objects in a retired list, local retired list, that to be later scanned for all those objects. And because this can happen, for chains of objects that become unreachable, we cannot guarantee a linear bound. An automatic memory reclamation must not only delete an object when it becomes unreachable, but also protect an object before it is dereferenced. I will start by explaining how our automatic pointer protection works before giving an example. For every arc atomic load and make arc call, it is created a temporary arc pointer object whose index is always HP0. The hazardous pointers array has an extra member called use that keeps track of how many local references use each hazardous pointer index. To each arc pointer object is assigned an index in the hazardous pointers array. An assignment between arc pointers will copy the published hazardous pointer if it is to be done on the same direction of the scan in the retired method, and the use variable is at 1. Otherwise, it will increment the use variable if it is positioned to the right. In case the arc pointer is positioned to the left, it will search for an empty position on the hazardous pointers array. So now how these rules apply while traversing a linked list. It starts by pref, cur, and next being assigned HP1, HP2, and HP3. Add load is published in HP0 and copied to HP1. Then
A is published in HP0 and copied to HP2. Then B is also published in HP0 and copied to HP3. Now Cur must be copied to Prev, but it is placed to its right, so it cannot copy A to the left, so it must increase the use on HP2. The same will happen for B. It must increase B, so HP3 to 2. Now it must search a position for next, because next at HP3 as a pointer, and it was used by 2 local references. So now it places, so C is published in HP0 and then copied to HP1. Now Prev is assigned Cur, so it has to increase use to 2, and HP2 is now available. Now Cur must be assigned next, which is C, but Cur is using HP3, which is in use by 2 as local references. It must search another pointer to the right of HP1, and it's HP2, and it's set to C. I will finish by showing our performance evaluation. We annotated Michael and Harry's lock-free linked list with PTP and OrcGC and compared them with hazard pointers and past the pointer memory reclamation schemes. The top graphs show results on an Intel machine and the lower graphs show results on an AMD machine. In a linked list, the hazardous pointers protection during the traversal of the list is the dominant factor. As we can see, on the Intel machine, the automatic pointer protector for OrcGC doesn't show any impact. This is because of the exchange instruction in the getProtected method that is present in all memory reclamation schemes. This is the bottleneck, and because of that we cannot see the impact of the extra code necessary to automatically protect the pointer. This is not the case on the AMD machine, where we can see a drop in performance for the OrcGC memory reclamation scheme. We also annotated Natarajan and Michal lock-free tree. This tree is never rebalanced. We ported the skip list present in the art of multiprocessor programming and annotated it with OrcGC. This skip list does not provide linear bound on the number of unreachable objects. Instead, it is bounded by key size. This is because of the contains operation that is to be wait-free, never restarts. We implemented our own skip list based on the skip list of the early INO, but now the contains operation restarts and the remove operation poisons the hard links to other that refer to other objects. This makes this skip list to give a linear bound on the unreachable of the number of unreachable objects, and the contains operation is now lock-free. Our skip list shows a skip list with the OrcGC shows comparable performance with the Natarajan and Michal tree. Consistently, the tree annotated with OrcGC is the one that performs worse. In conclusion, OrcGC is an automatic memory reclamation that can be used in acyclic algorithms. It can show 50% decrease in performance when compared with memory reclamation schemes. On the other hand, it requires simple annotation of the algorithms, and it can be the only solution for complex algorithms. It provides linear bound on the number of unreachable objects, and it can be used with any allocator and C++11 compiler.